Picture this. You've spent months designing a brilliant piece of hardware. It performs flawlessly on the bench, and you're feeling great about it. But then, you take it into the chamber for FCC or automotive EMC emissions testing, and you fail. Just completely fail. And the culprit? A single, seemingly benign cable. Honestly, it's one of the most massive, adrenaline-draining engineering headaches you can face. Well, welcome to this explainer. Today, we're demystifying cable shielding, heavily drawing on the definitive text by Henry Ott.
Look, this isn't just about checking a box to pass a test. This is a high-stakes engineering investigation. So why exactly did your design fail? Well, it's because invisible fields are literally turning your cables into antennas. By the end of our explainer today, you're going to absolutely master the fundamental physical reality of capacitive coupling. Plus, you'll learn exactly why the way you terminate your shield will either save your product or entirely destroy your sanity. Let's dive right in.
To really understand how this noise transfer happens, we've got to look past the surface of those physical wires and zoom straight into the invisible physics at play here. Check out the physical representation of two parallel conductors on the left side and then its equivalent electrical circuit over on the right. So conductor 1 has a noise voltage V1. Conductor 2 is our victim, the receptor circuit, and between them, bridging that physical gap, are invisible electric fields. Because these cables are short compared to a wavelength, we can actually model this coupling using normal network theory with lumped capacitance.
And that right there brings us to the core mechanism, mutual capacitance, which we call C12. Now, I want you to burn this analogy into your brain. Think of mutual capacitance as invisible rubber bands of energy snapping between the two wires. Every single time the voltage changes on wire 1, those little rubber bands stretch and pull, directly transferring that unwanted noise energy straight into wire 2. Now, C1G and C2G, those are just the capacitances to ground, but C12, that is the primary bridge where all the contamination happens.
So how in the world do we cut those rubber bands? Simple. We introduce a shield. Notice how adding a shield around conductor 2 fundamentally changes our equivalent circuit. By wrapping the receptor in a conductive shield, we've essentially built a Faraday rain gutter. Instead of the electric field rain from conductor 1 hitting conductor 2 directly, it strikes the shield instead. Because of this, the mutual capacitance is now divided into C1s, which is from the source to the shield, and C2s, from the shield to the inner conductor.
But guys, here is the absolute critical rule. A shield is completely 100% useless unless it's properly grounded. Seriously, if that shield is just floating there, it picks up the voltage from conductor 1, and since there's no current flowing through the inner capacitance C2s to drop that voltage, the exact same noise voltage just passes directly to your inner conductor. The shield voltage Vs absolutely must be forced to 0 by tying it to ground. Only then does your Faraday rain gutter actually do its job and funnel the noise away.
Okay, let's look at the math to prove this, because the math never lies. Here is Henry Ott's master fractional equation for the noise voltage Vn on an unshielded receptor. I know, it looks terrifying, but watch what happens. In almost all practical cases, the resistance R of your receptor circuit to ground is way, way lower than the impedance of the stray capacitances. Because of that condition, that massive, complex denominator just beautifully cancels out, and we're left with this perfectly elegant, simplified formula, Vn equals J times omega times R times C22I times V1.
Let me pause right here for a second, because this isn't just some academic exercise. As Henry Ott himself explicitly states in the text, this equation is the most important equation to describe the capacitive coupling between two conductors. This is it. This equation is literally your absolute blueprint for solving real-world EMC capacitive failures. Once you deeply understand this, you practically have the keys to the kingdom.
So, let's methodically break down what each of these variables actually means in physical reality. First up, Vn is your noise voltage. That's the actual failure you're trying to prevent. Then we have J, which just denotes the 90-degree phase shift that's inherent to capacitors. Omega is the angular frequency of your noise source, which is just 2 pi f. R is the resistance of your receiving circuit to ground. Then there's C12, that's our mutual capacitance, remember the invisible rubber bands? And finally, V1 is the magnitude of the source voltage that's causing all the trouble in the first place.
Now let's run through a quick, real-world calculation. Imagine your noise source, V1, is 5 volts at a fixed 10 MHz frequency. Let's say you have no shield, leaving a mutual capacitance, C12, of 10 picofarads. If your receiver circuit has a high resistance to ground of 10 kiloohms, and you plug those numbers into our formula, well, it yields a massive, test-failing noise voltage of over 3 volts.
Since you usually can't change the noise source's frequency or voltage, you have to manipulate the variables you actually can control. You either lower the resistance or you drop that capacitance.
And how exactly do we drop C12 if we don't have a shield? Physical separation. Take a look at the exponential drop in this logarithmic graph. As you increase the distance d between the wires relative to their diameter, the mutual capacitance just plummets. Doing this can take that 3 volts of noise we just calculated and smash it down to mere millivolts. It's a huge difference.
But there is a physical limit here, and this brings us to a critical takeaway from the text, the number 40. Spacing your conductors a distance greater than 40 times their diameter, which, for reference, is about 1 inch for standard 22-gauge wire, yields almost zero additional attenuation. Seriously, at a D over D ratio of 40, the curve basically flatlines. Moving those wires 3 inches apart really won't buy you much more noise reduction than just moving them 1 inch apart.
Now we pivot to the ultimate gotcha. This is the exact trap that catches so many hardware engineers. You followed the rules, you added a shield, you grounded it to decrease C12, but you still failed radiated emissions. Why? Well, comparing these two configurations reveals a stark difference. On the left, configuration B, a perfectly terminated 360-degree shield connection to the enclosure. But on the right, configuration D, the dreaded pigtail connection, where the shield is gathered up into a single wire and grounded at a single point.
The difference in the physics between these two is just astounding. With a true 360-degree shield, the common mode current flows down the inside surface of the shield and returns perfectly and safely to the source right through the enclosure. The net current is zero, absolutely no radiation. But a pigtail? A pigtail is effectively an inductor. Because of the skin effect at high frequencies, the current path on the outside of the shield is capacitive, but the path through that little pigtail you made is highly inductive. Think of the pigtail's inductance like a massive roadblock for high-frequency square waves. Those high frequencies hit that pigtail roadblock, realize they can't get through, and they are literally forced to turn around and flow down the outside surface of the shield through parasitic capacitance. As Henry Ott so perfectly notes, the length of your pigtail is effectively a rheostat, a volume knob that you're just turning up to increase the amount of radiated emissions. By using a pigtail, you've essentially just turned your perfectly good shielded cable into a giant radiating antenna.
Okay, let's do a rapid-fire recap of the essential rules you need to survive your next test. 1. Vn equals j omega RC1 2V1. That is your absolute master mathematical relationship for capacitive coupling. 2. A shield is only a Faraday rain gutter if you actually ground it to force the voltage to zero, otherwise it does nothing. 3. Physical spacing maxes out at about 40 times the conductor diameter. And 4. Never ever use pigtails for high-frequency shields. Use full 360-degree terminations or you are absolutely going to radiate.
You now have the mathematical intuition and the physical rules to go back to the lab and fix that failing test. But I want to leave you with a thought to chew on. Ask yourself, if an invisible electric field can turn a perfectly good cable into a massive antenna, what else on your PCB layout is secretly sabotaging your design right now? Don't let invisible fields control your product. Take command of them. Make sure to hit subscribe for more EMC and automotive communication protocol survival guides. Keep building, stay curious, and I'll catch you in the next explainer.